All right, 2-2. The topic of the day is normal curves. Big idea for us in this class. We're going to do some straightforward normal curve stuff early on right now, but our entire second semester is based on normal curves, so let's do it. We talked in the last video about the normal distribution, the bell curve, and we talked about these specific percentages shown on this graph to the right. 68% of our data will fall within one standard deviation of the mean, 95 within 2, and 99.7 within 3, which means that in a normal distribution, almost all observations will be within 3 standard deviations of the mean. Now, not every distribution is normal, but this applies to ones that are, and certain things just naturally behave in a normal way, and we'll talk more about those. The picture on the left is one I just found on Wikipedia that breaks down those percentages a little further, and you can see that they aren't exact. Different books will have different breakdowns, but those ones in blue there you can use to answer questions in 2-1 like this. All right, here's an example of a normal situation. The lengths of the catfish at Leroy's Catfish Farm are normally distributed, mean 27 inches and standard deviation 6 inches. So we talked about the notation a little in the last video. We would note this in 27, 6, which means a normal distribution, mean 27, standard deviation 6. So if we're going to put that on the graph, what that means is 27's right in the middle. All right, your average is 27. Move that down a little so we can see it better. And then we're going to just add 6 at a time. So 27 plus 6 is 33, then 39, and then 45, and minus 6, 21, and 15, and 9. So what does this tell us? This gives us some info. This tells us what proportion or what percentage or what probability is associated with a certain length range. All right, if I can answer questions like this. What's the probability that the next fish I catch will be between 15 and 33 inches? Well, 15 to 33 inches would be this section of the graph. And so I just add up the 3 percentages associated with those 3 sections. So those 2 middle sections are each 34.1, as you can see up here, and then the 13.6 for that section on the left. And I add those 3 numbers together, and that's the probability that the next fish I catch is between 15 and 33. So that's a pretty powerful thing to be able to do. You can find what percentage, last video we talked about the weights of newborn babies. What percentage of babies are above 8 pounds, or what percentage of babies are between 6 and 7 pounds, and so on. So that's something, and we've done problems like this in class. Here's the limitation where we are right now. What's the probability that the next fish I catch will be between, let's say, in order to keep a fish and take it home and eat it for supper, it's got to be at least 31 inches long. Okay, fair enough. Well, what's the probability that the next fish I catch will be above 31 pounds? Well, 31 pounds is right here. So I'm looking for all of this area greater than 31 pounds. And right now we're limited to only answering questions where the ends of the intervals in question are at a whole number steps from the middle. I can only deal with 9, 15, 21, 27, 33, 39, 45. I can't deal with 31 right now. That's a problem. Now, if I'm Leroy and I'm interested in this, I could make a chart. I could figure out every single possibility and put them all in a big chart and have that, but we're not going to have to do that. Here's the steps to answering a question like the greater than 31. This beauty right here, which you will have in your book, it's in every stats book ever written, probably. You'll have one on the stats test. This gives us all possible areas down to the hundredths place at every possible step along the normal curve. So here's what's happening. Let me go to the next page. I'll refer back to this one. That one that I just showed you, that's called the standard normal curve. In the middle of the standard normal curve is 0. The standard deviation on the standard normal curve is 1. So the standard normal curve looks like this. Now, why have a standard normal curve? All of these values stand for areas under the standard normal curve. For instance, if I go to the z-score, excuse me, you don't know what a z-score is yet. If I can go anywhere I want under the standard normal curve, and I can find that area. I could be at, negative 1.36 up to, 2.17. And that chart's going to allow me to figure out that area right there, which is going to allow me to answer questions like the one I brought up earlier. All right, so what's happening really is this. There are millions and millions of normal situations in the world. Okay, there's one for Leroy's catfish. It's got a certain mean and a certain standard deviation. There's one for the weights of newborn babies. These all are, they're all bell-shaped, they're all bell curve, but they're different heights and different widths of bell curves. But maybe this is the one for baby weights and so on. You get the idea. I'm just going to make different curves everywhere. This one could be one for the heights of all the oak trees in the world. There could be another one that's the, number of times a chocolate lab barks during the day. Whatever, acts in a normal way. It would be nice if there were one of these. Actually, it wouldn't be because there are millions, but one possibility would be to have these charts for every single situation. There could be the baby chart and the oak tree chart and the dog barking chart. There is one chart, and it's the standard one. So what we're going to do is standardize all of these so that we're able to look up the probabilities, or the percentages, in that chart that we've been looking at. So what I'm going to show you quickly are the steps to standardizing. Let's use this example, the one I was referring to earlier. I was talking about Leroy's catfish, and I wanted to know what percentage of them are over 31 inches. All right, and that doesn't fall at one of the even steps left or right, so we're going to have to standardize to end up using this chart. So here's the question. I don't know what you've written down with all these graphs and stuff, but start here definitely writing down, no matter what you've written down thus far. All right, so first step. What we need to do is find a z-score. A z-score is just a standardized measurement, and it is the number of standard deviations away from the mean. Make sure you write that down. And that's mu again, that's our symbol for mean. The number of standard deviations away from the mean is called a z-score. If it's negative, that means you're below the mean. If it's positive, you're above the mean, and these will rarely ever get above 3 or below negative 3. So to find the z-score, there's a simple formula. X minus mu over sigma. Sigma, lowercase sigma, that's that symbol on the bottom. That's standard deviation. I know on your calculator we use usually S for standard deviation and X bar for mu. The difference is these are population figures, and we can talk more about that later. But to find the z-score, we take the X value, which is the raw score, the real world number, 31. We're going to subtract the mean, 27, and we're going to divide by 6. All right, so 31 minus 27 is 4. 4 divided by 6 is 2/3. 0.666666. Let's call it 0.67. Always round z-scores to 2 places. Write that in your notes. Always going to round our z-scores to 2 places, and I'll show you why in just a minute. Step 2. We need to sketch the area that we're looking for. remember, underneath the normal curve, an area corresponds to a percentage or a probability. So let's just draw what we're looking for. Okay, I'm looking for, I'm not going to add this to my current picture, but remember my old picture. I'm looking for all of the area from 31 up. This is what I need. Okay, since I standardized, 31 is just a different translation of 0.67. So what I'm going to do is I'm going to draw 0 in the middle. I don't have to get real detailed with this picture. I'm going to go 0.67 over, and imagine the whole right side is basically 3, so 0.67 would be reasonably right here, but that doesn't matter a whole lot. Okay, this is just an, saying what percentage are above a z-score of 0.67 is the exact same thing as saying if that's 27 and that's 31, what percentage are above 31. It's just now that we're standardized. I don't have a chart to go to for catfish. I do have a chart to go for standardized lengths. So let's look at that chart. I want all of the area to the right of 0.67. Let me get rid of those for now. Here's how this chart works. And like I said, this is in your book. You'll have a copy of this paper. You'll have this for your AP exam. All the area to the right of 0.67. This chart gives me the area to the left, so I might have to do a little creative subtracting. 0.67, we're always going to round to two places. Let's find 0.67. This, we're on the right-hand side, so we're on the right chart because this is a positive z-score. 0.6 is here. 0.60, 0.61, 0.62, 0.67, we're right there. And I realize this chart might not show up real great on the video, but this is the area corresponding to 0.67. And I'm going to have to pause to actually read that because I can't read it on my own paper. Hang on. Okay, that's 0.7486. So what that tells me is if I go to a z-score of 0.67 on the normal curve, 0.7486 is to its left. These numbers are all to the left as shown in this picture up at the top. 0.7486. So what that tells me down here is that 0.7486 is all of this area. Okay, so now I'm going to just have to use a little insight to figure out what the area is I'm looking for. Remember, I'm looking for the green shaded area. The key is the whole thing's 1. So I need to subtract 0.7486 from 1, and that looks like it's going to be 0.2514. You can double check me there, but I believe that's it. So what does that tell me? If I go fishing, I pull out a fish, there's about a 25% chance that that's going to be over 31 inches. I'm going to be able to take it home and eat it. All right. The fact that the chart is always based on the left, you're going to have to sometimes subtract from 1. You're going to have to sometimes subtract 2 numbers that you find on the chart. And we'll do more examples like that in class, but I just wanted us to get through 1. All right. So that I should keep my steps going. That is step 3, to calculate the area. All right, and we did 1 minus in this case. So just to quickly refresh, if we have a normal distribution question, what we're going to do, we're going to take the numbers given in the problem, turn the raw score into a standardized z-score, because we only have a chart for that. We're going to sketch, and I know after we've done this for a little while you get tired of sketching, but you need to do it anyway. Sketch the area that you're looking for, use the chart to look up your value, and then sometimes subtract, sometimes not. Like I said, we'll do more of those. So this is a normal calculation. All right, I will see you in class. I'm out.